Hello and welcome to the Resilient Communities Libraries Respond to Climate Change panel with the Davenport Library. This has been funded by a stipend from the American Library Association. We've assembled a panel of experts to help raise awareness and provide accurate information about the climate crisis. They will show us the science, and there will be a time for Q&A at the end. I should remark that if you don't want your likeness to appear on the YouTube, on the YouTube recording, you can change over to your initials. You can hover over your name in the participants area, hit more, and click rename, and change to something nondescript, such as your initials or what have you. Also, turn off your cameras and mute your microphone if you don't want to have your video or audio transmitted. If you don't feel comfortable unmuting and speaking, put your questions in the chat window and we will read them without names. So without further ado, I'd like to introduce our panelists in the order that they will appear. First, Alex Morrison. Alex Morrison has a bachelor's degree in meteorology from Valparaiso University. She received her master's degree from the University of Iowa in civil and environmental engineering with a focus in sustainable water development. She has completed research on global climate models' ability to accurately produce extreme precipitation at varying timescales. She has also done research on the projected changes in extreme precipitation through the end of the current century. Alex has been working for the U.S. Army Corps of Engineers for almost 2 years, where she has worked on climate change assessments, flood modeling for the Iowa River, and is a member of the Clinton area flood team. Our second presenter is Jessica Brooks, a service hydrologist at the National Weather Service in the Quad Cities. She was born and raised on a farm in Northeast South Dakota and went to college at the South Dakota School of Mines and Technology in Rapid City, South Dakota. Before coming to the Quad Cities, she previously worked as a meteorologist for the National Weather Service in La Crosse, Wisconsin, and North Platte, Nebraska. In these 2 jobs, she learned to love the work involved in hydrology, which brought her to the Quad Cities in 2015. Our third presenter, Dr. Steve Bennett. He grew up in Cedar Falls, Iowa, and earned a BS in geology at the University of Northern Iowa. He completed his PhD in geology at Indiana University in 1994, after which he was hired by Western Illinois University and has been teaching there since. He teaches courses in geology and in the past, environmental studies. His specialty is water resources, specifically surface water and groundwater. Our fourth of 5 presenters, Amy Kay, has been involved with stormwater management for 13 years and has served as the clean water manager with the City of Davenport since 2016. Here she directs the resource conservation and watershed management programs along with activities of the Clean Water Program in compliance with NPDES and MS4 permits. She holds a Master of Arts from the University of Illinois Springfield's College of Public Affairs and Administration in Environmental Management and Planning. And last but not least, Nicole Gleason, as the City of Davenport's Assistant City Administrator and Director of Public Works. Nicole Gleason manages the complex programs and services of Public Works' 15 divisions and over 350 employees, including the city's flood plan. Prior to her current position, Nicole held the position of Logistics Manager and Assistant Public Works Director for the City of Davenport from 2014 to 2016. Before coming to the city, she held multiple positions in the supply management field at John Deere and Denso Manufacturing. So without further ado, I'll kick off this panel with Alex Morrison.
Okay, so thank you for the wonderful introduction and hosting this today. Let me get sharing my screen. Hopefully you guys can all see this now. Okay. All right, so I'm going to kind of start off our panel by discussing changes in precipitation And to really start talking about precipitation, we really need to first start talking about changes in temperature. So 2020 had tied with 2016 for the warmest year on record. I'm going to play this video that NASA has made. This actually, you should see this will be the last image showing the average temperature anomalies for 4-year ranges. This is 2016 to 2020. You can kind of see where we're going to end up. This video shows their entire record starting from 1880 all the way up to 2020, showing the different anomalies. This also gives a little more information about climate change and how 2020 was a record-breaking year. So hopefully this plays okay. If not, hopefully you can kind of see most of the images. This play, it's pretty short here. So there you go, that's it. And like the video said, 2020, we saw lots of records broken, record low sea ice, record high fires, record high hurricanes, record high temperatures, just crazy records being broken. There we go. And so the last 7 years have actually been the warmest 7 years on record. And I put a little box here showing the last 7 years, and it's pretty obvious that, yeah, it has warmed a lot over the past century, and it's likely going to continue to warm. So what does this have to do with precipitation? Well, as average temperatures at the Earth's surface rise, more evaporation occurs, which in turn increases overall precipitation. Of course, this is not always the true fact. What we have kind of been seeing is that in places where droughts and extreme heat are common, they're experiencing more droughts and more extreme heat, while in other areas where extreme precipitation and flooding is more of an issue, there is now more extreme precipitation and more flooding. And we can kind of see that trend in the Midwest as we kind of continue here. So average temperatures are rising in the Midwest. This kind of shows temperature anomalies over the past century. And from the trend line, you can see that there has been a very distinct increase in temperature in the Midwest. And considering the Midwest often has a very distinct flood season and a lot of extreme precipitation events, it's not very surprising that we've also seen precipitation anomalies, and meaning overall average precipitation also increasing. From this chart here, you can see that precipitation anomalies have increased by almost 4 inches, which is quite a lot for precipitation. Looking more seasonally, kind of understanding seasons, precipitation has also increased for every season in the Midwest. And more specifically, the largest increases are seen in spring and fall, which also happen to be the 2 seasons where we have the highest amount of precipitation typically, and also usually see large flood events. So it's very concerning that these are the 2 seasons where we are seeing precipitation increase the most. Looking now even more locally, you can see on the right here, this is kind of the trend for the central eastern part of Iowa, of course, where Davenport is. And it shows the trend over the past century or so, showing that precipitation has increased by almost 5 inches over the past century. Now, on the surface, 5 inches doesn't seem like a huge amount, but we're not talking about just in one location. We're talking about an increase of almost 5 inches across this entire region. And that's a lot of water going into the area. Just touching a little bit on what projected changes look like. If we look at model results, this map here shows the projected change for 2041 through 2070. This shows that precipitation is likely going to continue to increase. And if you look just kind of locally in the Quad Cities region, it's likely to increase by 4+ inches. And we've already increased by almost 5 inches. So this is a lot of water coming into the area, and it's very clear that heavy precipitation is going to continue to be an issue. All right, so I wanted to talk about this as a Corps employee. I can't talk about extreme precipitation without talking about what happened in spring of 2019, because this is a perfect example of what happens when you have above average precipitation for a season or 2 seasons, combined with infrastructure problems and how that can cause record-breaking flooding. So the setup for this event, accumulated precipitation that winter, so this is snowpack, was 150 to 200% of the mean. So that is way above average what is typically seen. And I've provided this map here on the right, so you kind of get an idea of where rivers are. Jessica will kind of get into more on stream flow stuff in her presentation, so I just want to touch on this a little bit. Basically, my point with showing it here is when all this snow melted, it didn't all go into the ground. A lot of it went into tributaries of the Mississippi, went into the Mississippi and made its way down to the Quad Cities. And that was a big reason why the flooding was so severe. To give you more of an idea of what this looks like in terms of melted water and not just snow, here is a map of modeled snow water equivalent for February when things were starting to melt. And you can see in this kind of general region where we're looking, it ranges from 1 to 6 inches of water. And combined over this entire area, that's a lot of water going into the system and making its way through the Quad Cities. On top of this, when the breach actually happened, during that week, there was a lot of rain. This map here shows accumulated precipitation. In this case, it was rain by this point because it was spring during the week of the breach. And the breach itself happened on April 30th. And so you can see just in our region, there was 4 to 5 inches of accumulated precipitation that week, which is a lot of rain on top of an already high river due to a lot of snow melt. This year, and hopefully this one plays decently too, is a video of the breach. And so you can kind of see from this image how badly this was if you haven't already seen this video. So the area to look at is this upper left corner is where the breach happened. And you'll kind of see the barrier. It starts to kind of slip and slide and tip. The water starts to pour over in one spot. And once it started to pour over in that one spot, it just spread and collapsed a huge section of the barrier. And so it immediately started pouring out into this area and starts filling up this area. And you'll kind of see in this video, as soon as people start to realize it, there's a lot of rush to get out of the way because there was really nothing that could stop it. I'll kind of skip through a little bit because this is a long video. We won't watch it all. So finally, as the water kind of pooled up in the area and then continued out into this parking lot, and eventually after filling up this area, it continued and flooded most of downtown Davenport, as you saw in that first aerial image I showed of the flooding. I'll skip a little more. And so, yeah, it got really high here. There we go. So we don't have to watch the rest of the video. This is kind of where it ends up. It was several feet of water that ended up, high in downtown. So it was a big problem. So why exactly did the barrier fail? Well, first, here is a nice image again of kind of where the barrier was. So this yellow line represents the barrier. This red here is where the breach happened, and it kind of spread out around here. So that's how that looked. Okay, so why did this barrier fail? Well, ultimately, they discovered it really wasn't an issue with the barrier. It's HESCO baskets. It wasn't a problem with the HESCO baskets themselves. It was a problem with friction, and the force of the river on the barrier ended up being too great and overcame its weight, causing it to kind of tip and just collapse. Excuse me. So typically how these baskets work is they're collapsible, they're nice portable, you set them up, fill them up with sand, and then they just act as a temporary barrier there for the water. But the issue with this event is the river had been high for so long, plus there had been heavy rainfall on the day of the breach, causing the pavement to be wet, and water was able to seep under the barrier, which reduced the friction enough for the barrier to slide. And because the river had been high for so long, the weight ended up finally forcing the barrier, causing it to collapse and slide. So again, this really wasn't a problem with the HESCO baskets itself. It was a problem with how they were set up. The Corps inspected like what exactly happened, and they found that the baskets are typically supposed to be set up. You have the main row, and then you fill them with sand, and then you have a second row behind it that you fill with sand as the flood becomes worse, as extra weight to keep the barrier in place. Then as the river gets higher and higher, you can stack more baskets on top to accommodate for that higher level of water. This was not what was done. And so they only had the one wall that was very easy to slide and slip. And you can kind of see in this image, another issue they did was they filled sandbags and stacked it on top of the barrier, which disrupted the center of balance and weight of the basket and made it easier for the water to disrupt it and tip it. Excuse me. So this brings up the question of, will these baskets be enough in the future, or do we need more permanent infrastructure? And this is a big debate in Davenport. In Davenport, you know, we take pride in the fact that it's open to the river. You can easily walk up, dip your toes in the water, and enjoy the beautiful view of the river. But when it comes to flooding, this isn't very safe and doesn't offer much protection. This is why they have the temporary barrier with the HESCO baskets, but it's clear if they are improperly used, it doesn't always offer enough protection. And as flooding becomes more frequent and worse, as we've seen there's going to be more extreme precipitation, so events like this are more likely to happen in the future. So it begs the question, do we need more permanent infrastructure? Do we need to finally build that flood wall or a levee to help protect downtown Davenport from having another levee breach like this one? And honestly, I will say I do not know the answer to that question. It's a hard debate. I know I'm someone who really enjoys being able to walk along the river. It is very beautiful and nice, but it also has that risk. And considering that flooding is likely to become more of an issue, and we've seen so many floods in the last decade in Davenport, it really is a question of what should we do? Okay, so quick summary, some main takeaways I want you to get from this. Precipitation has drastically increased over the last century, not just locally, but in the Midwest. And I didn't really show you it, but in the United States too, the precipitation has increased. And from what models have shown us, it's likely that precipitation will continue to increase. And so in Davenport in particular, issues with flooding and extreme precipitation events will likely continue to be an issue and continue to become more of a problem. And so the question arises, do we build permanent flood mitigation infrastructure, or do we continue with the temporary means that we have? It's a hard question, and it definitely will be a topic for debate and discussion probably for years to come before we actually end up with the decision. But for now, that is all that I have for today. I hope you enjoyed this. Here is my contact info. Email is the best way to contact me if you have any questions or other input about this. So thank you.
And with that, I guess we'll turn the floor over to Jessica.
Okay, give me 1 second here. All right, I believe screen is being shared. Someone give me a thumbs up. Okay, perfect. All right, so again, my name is Jessica Brooks, and I'm the service hydrologist in the Quad Cities National Weather Service office. My job is really based on forecasting river levels, as well as forecasting the weather. But I am our hydrology water river person at our office. So some of the things I have today are my first couple of slides actually are going to be kind of some of the same things Alex was talking about, so I'll be able to go through them pretty quickly. But anyway, so the data that scientists have been looking at for years is showing us that across the upper Midwest, we're getting warmer, we're getting wetter. We are seeing less snow across our part of the country. And then we're also getting more stream flow happening. So when we're looking at river levels and forecasting river levels, the things that we really look for are how much rain is there in the system or in the area, how much snow have we received, what are the temperatures, we look at the soil moisture, and then we also look at soil characteristics, land use. So it's not all about the rain and the snow and the temperatures, and you do also have to consider the characteristics of the soils and how the land's being used, because that will impact your stream flows. So I won't talk on this a lot because Alex did. But again, this is a graph just showing how our temperatures have been increasing over the past century and more than that. So, and the thing with temperatures increasing, the air can hold in more water. Warmer air holds in more water. So when we have when our temperatures rise by a degree or two, that doesn't seem like much, but that degree or two can hold additional water and up in the air. And when you have more water up in the air, that means you can have more rainfall, is kind of how that all goes together. So looking at our precipitation trends, again, this is what Alex touched on too. This is for the upper Midwest. Just showing, you have a lot of ups and downs as you go through the years, but overall your trend is going up. And this, the kind of smoother line is a 30-year average. So showing that's going up. And obviously the last, since 2000, you're seeing that line go up at a higher pace. Again, looking at our seasonal trends, so we're seeing increases in every season. In fall in particular, fall and winter are typically our driest parts of the year. Spring and summer are our convective season, when we see lots of thunderstorms, when we get our spring rains. So those are our typical times a year that we see a lot of precipitation. But again, we're seeing these increases every season. But the fall one is the really big one that we're kind of noticing a different trend and seeing more fall floods happening. So on the right side of my screen is just showing some of the things that we're kind of expecting, things that we've been seeing the trends of and expecting those trends to continue into the future. So the northern part of the basin, so the green circle, so in the background you see in the yellow is the upper Mississippi River Basin. So everything that drains into the Mississippi River above St. Louis is what we're considering really. So the area in the northern part of the basin, we're looking at, there is potential for more snowfall. So that kind of is a little different from what I said in the first slide, saying less snowfall. So the less snowfall meaning in our area. The upper parts of the basin could be seeing more snow into the future. So you're looking at warmer temperatures. So the air is able to hold in more moisture, so you can get more heavy snow events. Across the southern part of the basin, so in the blue circle, we're seeing trends of more of our cold season precipitation coming as rain rather than snow. And that trend, so if anybody who's lived in the area, you can likely say you've noticed that over the last 10 years or so. Once, we have way more rain in December and January than, you've seen in years past, where typically you're in winter, any precipitation, snow. That's not necessarily been the case. And that is a trend that you would expect with a warming atmosphere. So now talking about actual river flows. So what I have here on the left is our stream flows, and it's looking at every point through the year from the late 1800s through 2020. And when you look at this, it's a lot of colors, but really what your eye wants to be drawn to is the greens and the blue colors. Those are the high flows that are being measured. And this is at the Mississippi River in Clinton, so just upstream of the Quad Cities here. So as you would expect, the March through July timeframe is where you see a lot of the greens and the blues, the high stream flows. And that's in our spring season, that's our wet season. But if you notice on this area in the top right that I have in a box, that's since about 1970 and the 1980s, where you see a lot more of that green in the fall time frame, the fall and early winter, as I kind of alluded to earlier, that we're seeing more precipitation coming in the fall months. So typically, if you look previous to 1970, you might have a few years here and there where you have higher stream flows in the fall, but it's much more condensed, and you're seeing a lot of that here over the past 40 some years. And on the right image, that's just a zoomed in visual of the 1960 to 2020 timeframe, where you can see a lot of those higher stream flows occurring in the fall months. Now, looking at our annual discharge, so the black line on this graph is showing your stream flows through the years, and this is going back to 1930. And again, you see ups and downs. You have years that were definitely lower stream flows. And this is our annually the amount of water that goes by that river gauge. And again, this one is at Clinton, Iowa. And so you see the trend is definitely going up. The red dots are our 30-year average. But the thing to really hit on is your stream flows are higher. There's more water going by this gauge on average through the year. Then I also wanted to show you at St. Louis, so going down to the lower end of the upper Mississippi Basin. So the trend is the same. It's going up, and then in St. Louis, that's where you're getting input from additional rivers. So it's not just the Mississippi River, but a larger part of the landscape of the country. But the main theme is the flows are going up. We're seeing more water moving through the Mississippi River. So looking at precipitation, I'm bringing this up because I'm going to give an example here in a second. So looking back to the late 1800s, your trend is going upward of the annual precipitation, and this is for the entire Mississippi Basin. And so I want to hit on 1942. So prior to 1970, 1942 was the highest amount of precipitation we had in a year across the upper Mississippi River Basin. So again, that's everywhere upstream of St. Louis. Once you get to 1970, you see a lot more peaks higher than that. But prior to 1970, 39.09 was how much precipitation fell. So looking at our annual runoff, so these are a bunch of lines here, but to explain what you're looking at. So 1942 is your purple line here. So again, prior to 1970, that was a high year precipitation. That was a really wet year. This darker blue line is 2019. So you see a lot of difference there between 1942 and 2019. And this lighter blue is 1993. So the other lines you're seeing here is how much we're normally seeing. So the gray line is your 50th percentile. The green line is your 75th percentile, and the orange is your 25th. So most years you're going to see your annual runoff in the region between those lines. So you see 1942 was actually around your 75th percentile. But as you see, 1993 and 2019 are well above those numbers. And just for reference, 1934 is our driest year and had the least amount of runoff across the region. And I guess I didn't preface this, but runoff would be the amount of water that's not soaking into the ground, the amount of water that's actually moving across the landscape and into your rivers. So the point I want to bring to this is in 1942, we had 39.09 inches of precipitation across the region. Out of that, a little over 10 inches was direct runoff into your rivers. So you had almost 29 inches of that absorbed into your landscape. In 2019, we had more precipitation, 45 inches, and 20 of that was direct runoff. So you had 25 inches, a little over 25 inches absorbed. So the thing that I want to bring up with this is 2019 versus 1942, we had 6.19 inches more precipitation in 2019. However, you had over 9 inches more runoff. So you would think normally that those numbers should be equal. If you had 6 more inches of rain, you should have 6 more inches of runoff, but your runoff was more. So that brings you to the question of what's happening. Is this a land use thing? Is this, are there infrastructure changes that are bringing this about? Is it the way the rain is falling? Are we getting, is it more rain versus snow? Because when you have snow, you're probably going to get a little more absorption from the snow than the rain. So there's a lot of things to consider here, but the main point is we're getting more runoff, and meaning higher stream flows across the region. And then quickly, just to touch on our flood history. So I have Clinton, Iowa, Rock Island, so the local gauge here, and then St. Louis. What you're looking at are the top 15 flood years across in these 3 locations. The bolded numbers are in since 1960. The ones in yellow are in the last 30 years, so since 1991. So in all 3 of these locations, you see a lot of our top 15 floods happened in the last 30 years. So that's pretty significant. And so here's my contact. I want to say a big thanks to Steve Bennett and Ray Wolf. They are some coworkers of mine and helped me put these slides together, and I kind of stole some of the slides from them from other presentations that they've done. So anyway, that's what I have, and I will let us move on to Steve, I believe.
Were you just wanting me to start, or were you?
That was such an excellent introduction. She tossed it so seamlessly to you.
Oh, okay.
I'd like to welcome Dr. Steve Bennett.
All right. Well, let me get this all share it up for you. All right. Am I good? See it? Okay, so good morning. It's still morning, isn't it? Yeah, it's before noon. So yeah, I did not get to experience that huge flood that Alex showed so nicely in the first presentation, because I'm down in Macomb, where you know, we're far from the river, but we're perfectly aware and get called in. Some of my colleagues from the GIS Center during that 2019 flood were going south, not north, but along the river. So I'm a geologist. We think really big picture and long-term things, and starting from kind of very first principles. So what the heck is a flood? I mean, we know it's just water leaving its channel. Do humans make floods? No. They're natural. They occur. They're always going to happen. I love this image because it actually ties into what some of the things you had just mentioned earlier about how in St. Louis we have this confluence of rivers. Here's the drought year of '88. I remember how dry that was. And you can see how small the Missouri, the Mississippi, and here's the Illinois River were. And then here in '93, you can see the entire floodplain covered by the Mississippi, the Illinois, and even down here in the Missouri area. So if they're natural, why do we care about them? Because we don't want things like this to happen if we can do anything to prevent it. We know that they mostly occur during the spring. Why do they mostly occur during the spring? Although, as Jessica just pointed out, they're getting more common in the fall than they had been in years past. That was a very interesting graphic she showed. A couple of reasons, and some of them are going to tie into the image I show, but things that allow the water to run off more quickly are the fact that in the winter, sometimes there's still snow on the ground, and the spring rains might fall on that. It's a wetter time of the year. The ground might still be frozen in some places, maybe not around the Davenport area, but what about up in Minnesota in the northern part of the drainage basin? It's falling on frozen ground and the water can't even infiltrate, regardless of what kind of soil it is. So that's why it's more common to get them in the spring, not that they can't occur at any time. So since they come in a lot of sizes, we have tried to come up with ways of ranking them, right? And you've heard the term discharge. Remember, discharge is just the volume of water flowing past you at a given time. So when you hear that 10,000 CFS or cubic feet per second, saying if you're standing next to the stream and say 1001, you just had 10,000 cubic feet of water flowing past you. And just for reference, a cubic foot of water is 7.5 gallons. So imagine a 5-gallon bucket and another one half full. That's how much is in just 1 cubic feet. So it's a significant amount of water. One way of ranking the floods then is to look at a lot of times the biggest flood, the peak discharge that occurs in any given year, water year, I should say. And you'll notice the graphs earlier that Jessica was showing our water year starting in October 1st. And then you will look at a watershed, a stream section like the one in Clinton there over a period of time. And the longer you have to look at it, the more confident you are that any prediction of recurrence of a flood it'll be better. You have more data. It's always that way with statistics, isn't it? The more data you have, the more confident you are in your prediction. So 2 common recurrence intervals that you hear run into, if you're, say, looking at a flood map and areas that might be inundated after a flood, you'll see the 100-year flood and the 500-year flood. Sometimes they'll be hidden as frequencies, which is another way of looking at it. A 100-year flood means you have a 1% chance of a flood of that discharge occurring in any given year. Not that you couldn't get 2 of them in back-to-back years if you're very unlucky, right? A 500-year flood, which is something like when they're putting a new bridge up there in the Davenport area, you can guarantee they are engineering for the 500-year flood. So it's a 0.2% annual chance. So the question is, and this ties into the very nice graphics that were just in the last presentation by Jessica, we see that the discharge over time has been slowly creeping and creeping and creeping and creeping up. At that Clinton station, it was clear, and that's true about anywhere you look. So that means a 100-year flood that we would compute based on, say, the last 30 years of discharge data would be very different than a 100-year flood we'd based on, say, data from 1900 and 1930, right? So our what it's telling us is these extreme floods are occurring at a shorter time interval. Our 100-year flood is not the same as our grandparents' 100-year flood. Ours might be, that might occur every 75 years, maybe less. We'd have to compute it, obviously. So while floods are natural and they come in a variety of sizes, we also know that humans do impact the recurrence intervals. And these 2 things have already been addressed. So that's great. They're building on each other. I'm not going to address the second one, impacting the climate. Actually, Alex did a good job of showing how the climate is changing and tying it into the carbon emissions that we all know humans have been making since the Industrial Revolution at an increasing rate. Well, the land use, and again, Jessica mentioned that in her presentation, how that impacts their predictions of runoff. Let's talk a little more about that. I'm going to give specific examples. And the most easy to wrap your head around is just the fact that urbanization is occurring, right? If we look back in the 1930s, 40s, 50s on up, these suburbs that have grown up around all of our cities. And I'm sure all of you know places that were farm fields when you were younger, and now there's a strip mall there, or there's a housing development there. Well, what goes into urbanization? Roads, buildings, parking lots, less vegetation. These top three all involve impervious surfaces, don't they? And that means the water can't seep in to replenish the groundwater. I'm a groundwater person myself more than a surface water person, so that's extra troubling. But the less vegetation that commonly goes with urbanization, this might have been a prairie area in the distant past, probably was row crops, then put into suburbs. But in any event, there's less vegetation commonly than there was before. So what does that mean? If you have less vegetation, you're going to have less of this, less interception. One of the interesting things that I was thinking about in Jessica's presentation, she showed that dramatic difference in the runoff to precipitation from the 1940s to that more recent rain event year. And she commented that could it be more rain and how it fell? And yeah, those are really good questions. One thing that you can always look at is the timing of the rains. The same rain that falls in the middle of the summer when the crops are up and the leaves are out, not nearly as much of that will hit the ground and run off as what will happen if that falls in this time of the year when the trees are just leafing out, the crops aren't in the ground. You have much less interception. So what's the net result? Less infiltration, more runoff. And if you're going to have a lot more runoff, that means you might see your hydrograph. This is another way of plotting water versus time. There's a lot of types of hydrographs, water graphs. You might get a hydrograph that looks like this on the bottom instead of this on the top. So this is a real simplistic way of imagining it, but it's a good thing to think about, is if you're in an area pre-development and you were to speculate on how much rain might infiltrate versus run off during a rain event, you could have maybe 0 to 20% runoff and maybe 80 to 100% infiltrate in this situation. Whereas if it was a complete urban center like this bottom graphic where they've channelized the stream and they've got storm sewers, and we really want to get that water out of our urban areas as quickly as possible, you might get 90 to 100% runoff. Same rain event. So even without us causing bigger rain events, which climate change can contribute to, we're going to get more runoff with urbanization. So what does it mean? Well, the summary is more runoff and quicker runoff. So the hydrograph goes higher after urbanization, but also the lag time, we'd call it, between, well, kind of the beginning of the rain event or the center of mass of the rain event and the peak flow in the stream. There's more time here in a pre-development setting than there is during an urban setting. So we get more runoff and it gets there quicker. So we have flashier floods as well. Streams go up that much quicker. Now, not to just pick on the cities, I'm going to close, be quick on this, with how even outside of our cities, over the last century and a half, ever since we've started really putting in row crops, we've realized, and I've got brother-in-law farmers that attest to this, that you can really increase your yields. One of the cheapest things you can do is tile your field. And interestingly, the people, I live in the country, and the people just to the east of me were putting in tile just yesterday to get the water into the nearby creek, like this image is showing, as quickly as possible. Makes sense. They can work their field quicker. But one of the upsides of this as well that you may not have considered is that all of that tiling means that water that would have sat in the soil for longer before it gets to our streams gets there much quicker. You could think of them almost as rural storm sewers in a sense, because they are draining the upper water out of the fields out and bringing them into nearby streams. And this is from a property that WIU owns. And you can see not only is the water gushing out, But just in a side note, how much erosion, you normally wouldn't put this pipe that far out. It comes out so much, it has eroded the stream bank back as well. So that pipe is sticking out way further than it really should be. Okay, that is my quick presentation of how flooding in recurrence intervals can change over time due to human activities. All right.
We'll flip over to the municipal perspective now. Amy Kay and Nicole Gleason. Amy Kay is the City of Davenport's Clean Water Manager.
Good morning. Is everybody seeing the screen okay?
I think you still need to share.
Okey-doke. There we go. Is that better? Okay, well, I'm going to take us back up the watershed just for a little bit and talk about some of the things we do in Davenport as part of our watershed management program to help, reduce or at least manage those increased stream flows and amount of runoff due to development. One of those are with our, we have quite a suite of development regulations that help manage water and try to keep it on site or infiltrate it on site. And one is with stormwater detention, new development and redevelopment over a certain size requires detention on site. A lot of times that ends up being a detention basin of some kind or underground storage. And with that, we try to mimic the release rate that would have been there before, maybe when it was prairie. So the detention basins and underground storage areas will hold onto that water and meter it out at a lesser rate to kind of mimic those hydrographs that we saw from Steve, to mimic more of that forest or prairie floor instead of the paved surfaces. Along with that, there's water quality treatment, things like bioretention cells or even wet ponds that help reduce the amount of bacteria, hydrocarbons, sediment, and things like that that are getting into our receiving bodies are a requirement of new development and some redevelopment. We also have an illicit discharge detection and elimination program where we pursue illicit discharges that we find in our receiving waters, or if we see in the street that may get into the storm drains. We have a lot of floodplain management techniques, such as our stream buffer requirements that it's a 50-foot buffer requirement to let those streams meander or to let those floodplains or flood zones fill up when it rains. We also have a lot of community rating system standards for the National Flood Insurance Program, such as, having those buffers and having these other stormwater management practices will help with that program and reduce insurance rates for folks in the community rating system that happen to have structures in the floodplain. We also have some open space preservation codes, either in the stormwater management ordinance or in our zoning ordinance, that kind of dictate how much impervious surface versus open space you can have on a single property. And we work to increase or manage our open spaces along our Duck Creek corridor and our other greenway corridors and streams that we have in town. In addition, we have a lot of woodland and prairie management. As was discussed, the more tree canopy you have, the more interception you're going to have, and the more evapotranspiration you're going to have. Prairie plants have extremely long root systems that help create pores in the soils for better infiltration, and they also take up a lot of water. They help improve soil quality, which can hold more water and act more like a sponge. We used to be able to, in our prairie days long ago, we used to be able to hold on to about 6 inches of rain and now it might be less than 1 in certain circumstances. So with our Parks Department, Natural Resources team, and other groups, we're able to try to manage a lot of those areas. There are lots of acres, hundreds of acres, mostly along the Duck Creek corridor, but some in other areas that are in some level of management, reconstruction, restoration, or they've already gotten to that point, or they're in planning stages to try to keep those areas healthy and growing. We also have a host of cost share programs. So our 50/50 cost share we have available to anybody who pays into the clean water utility fee. So most businesses and homes, and I think just about everybody is involved with that program. And it's to install best management practices, or BMPs. And those, many are listed here, but it's not the inclusive list, but things like soil quality restoration, where you're increasing that organic matter that holds on to moisture. Rain gardens, which there's an image of here on the right, where you can direct water from your downspouts or home or driveway to try to get that infiltrated and percolated into the ground. Permeable pavers, green roofs, timber stand improvements, rain barrels, wetlands. We also have a stream bank stabilization cost share program, which is separate from the best management practice program, but a similar cost sharing mechanism to help private landowners stabilize their banks, even if there hasn't in areas where there is a lot of vegetation, or they do have buffers. That increase in stream flow, a lot of the vegetation along those streams just wasn't ever designed to handle those flows, and so sometimes they need a little help. If there's major erosion problems, we can help fix that, stabilize the slopes, prevent that sediment from running downstream, prevent property loss, and all sorts of other issues. We also have a big education and outreach program just within the city of itself, but then we also have lots of different agencies that we work with. And particularly, I wanted to mention the Partners of Scott County Watersheds. It's our main mechanism to reach outside of our jurisdictional boundaries. And so the Partners' main mission is to improve stewardship of the watersheds through education, technical guidance, and volunteer opportunities. The idea is that the more people understand how all of this kind of works together in a systems-wide perspective, and they realize that agriculture production and making a parking lot both contribute in different ways to flooding and water quality concerns, and the more we'll be able to work together to find some creative solutions. And so this is our way that we can work with the county throughout to kind of have that rural connection. We've got some production farmers and other folks that live in rural settings on the board of directors, and they help us connect with the NRCS and the Soil Water Conservation District to either spread the word about available funding in a rural setting or on ag lands, such as buffers, wetlands, or like end of tile wetlands. We saw that the image from Steve with a drain tile in their fields just going right out into the stream. There are lots of end of tile practices that you can implement on the farm to help treat that water and hold on to some of that water, just like there are in urban settings. And that's all I have. Just wanted to bring you up from the river just for a minute. I don't have my contact information here, but you can email the contact us at davenportiowa.com, all one word, and any inquiries about any of that information will get routed to the appropriate person.
Then we'll round things out with the head of Public Works, Nicole Gleason.
So hopefully you can see my screen here. All right. So basically what I wanted to share here today is what we're working on with HR Green. So after the record flooding in 2019, there was really a need to kind of look at the river as a whole and what Davenport's goals around the river were. As Alex mentioned, we did actually set up that second HESCO configuration with the 2x2 for the third crest in 2019, and did see actually significant pavement buckling behind the walls. So we do know that even beyond temporary or permanent barriers, there are definitely other underground infrastructure issues. And so a big part of this is educating people on what the challenges are and you know, different ways to handle the challenges, but also setting realistic expectations. So where we are with this process right now is we had some kickoff meetings, we had public input back in the fall, and we're actually getting ready to do a second round of public input now. So this is just similar to what we saw before as far as what the river has done and some of the changes that we've seen in Davenport specifically. And this study that HR Green is undertaking is using many different aspects, including land use planning, looking at our operations, because if we have our entire operational team working on the riverfront, they're then unavailable to fill potholes and clean sewers and many other things around town. So that's a big part of it as well. So this is just an example of some land use planning that takes flooding into account. So as they're getting public input, HR Green is sharing these types of ideas and seeing what the public would be amenable to in Davenport specifically. And then obviously some mitigation alternatives. So another part of this is we did use the services of the Silver Jackets with the Army Corps, and we did base floor elevation study on 1,100 properties, and we are letting property owners know where they are in the flood elevation. You know, are there options for protecting or flood proofing their buildings, raising their buildings? You know, is your building in an area that maybe a voluntary buyout's a better option? So it's a very inclusive process. And then this is just an example of the amount of resources it does take when we do have flood operations. So that top left picture there is setting up the metal wall around Modern Women Park. And then that top right picture is the 2x2 HESCO. So not only is it very labor intensive initially, but then the cleanup effort after the fact is quite intensive as well. Another big focus of the study is transportation and mobility. So obviously when River Drive's closed, we start having access issues to our bridges and things like that. So a big part of this study is also trying to make a much more defined flood route through Davenport and trying to help people traverse the town and keep as much of the town open and accessible as possible during flood events. And then finally, obviously, nothing's free, unfortunately. So as we get that information back from the public on what they best want to see, you know, different options, you know, a large pump is a very different cost than a large flood wall. So as we look at what those final recommendations are, how would we actually fund these things? So, and obviously there is a lot of federal funding out there right now, and we are actively pursuing those things. So just really wanting the public to understand this is high on our radar. We are taking it very seriously, but unfortunately there's no easy answer. The answer of building a flood wall, I think people, when they think flood wall, they think, oh, you could build a 1/2 mile flood wall or a 1 mile flood wall. Well, Davenport has 9 miles of riverfront, and any point where the river can get behind the flood wall is basically then it's going to fill up like a bowl. So it's not kind of too much of a fragmented process. We really have to look at it holistically for people to understand what those challenges are. So I would really like to invite anyone who's interested in understanding what this flood study is, and if they're interested in giving feedback, this will be live, I believe, Monday morning. So this is really good timing to see what HR Green and Sasaki have done so far, give feedback and learn, you know, what some of these challenges are. So we really appreciate the opportunity to share this story and help, I guess, enlighten the public on what these challenges are. That's all I have.
Thank you very much. We'll open up the floor to some Q&A at this time. If you don't feel like unmuting, you could type it into the chat window and we'll review that. Would anybody have a query for one of our panelists or all of our panelists?
I have a question for Jessica.
Sure.
On one of the graphs that you showed, of course, all of them are increasing trends just across the board. But one of them, I noticed that in the 2020, there was a 45-inch annual precipitation. Is that, do we have an average now over the last 10 years? I mean, obviously it's increased, but what would that average number be?
I'd have to look that up to see what that actually.
Okay.
Yeah, I mean, I can try to interpolate off the graph a little bit. Let's see. So we are right, probably about 30, average is probably between 35 and 36 inches right now. And then that's kind of that average trend line where we would be. Where yeah, you know, in 1942, again, that was a wet year, we had 39 inches, and that's across the whole basin. So that's kind of your average, and that's the statisticians do those calculations on how they get those exact numbers. But yeah, so looking from 2010 to 2020, that's kind of where we are. We're, you know, a little over 35, but probably not quite to 36 inches on average.
Any questions from the public? So with that, I guess I'd like to thank everyone for carving out an hour on a spring Saturday for us here. I'd like to thank the attendees and our panelists. It's been a long road. And of course, I'd like to thank the American Library Association's Resilient Communities Libraries Respond to Climate Change for awarding us this stipend to fund our speakers. And at the end of June, we will be using some of those funds to take care of about 30 or so folks to be on the new Nahant Marsh expansion area. They've just developed a berm for the additional 39 acres. So there'll be a guided tour of that. Look on our website for your free spot that will cover using those grant funds on that tour. So on behalf of the Davenport Public Library, thank you and have a good day.